Imagine a bridge, not one made of steel or stone that spans a river, but a bridge made entirely of water that spans a continent. Deep in the tropics of Central America, there exists a machine so vast and so complex that it changed the shape of the world map. This is the Panama Canal. It is not just a ditch dug between two oceans. It's a marvel of engineering, hydraulics, and economic power. For over a century, this water elevator has defied gravity, lifting the largest ships on Earth over a mountain range to connect the Atlantic and Pacific. Today, we deconstruct this mechanical wonder to see exactly how it works. To understand the genius of the canal, we must first look at the problem it solved. Before 1914, if a ship wanted to travel from New York to San Francisco, it had to undertake a perilous journey of nearly 13,000 miles. It had to sail all the way down the coast of South America, brave the treacherous waters of Cape Horn, and sail all the way back up. The Panama Canal changed everything. It is a 50-mile artificial waterway cut directly across the Isthmus of Panama. By slicing through this narrow strip of land, it saves vessels approximately 8,000 miles of travel. It is the ultimate shortcut, shrinking the globe and accelerating the pulse of international trade. However, building this shortcut was not as simple as digging a trench. The geography of Panama posed a massive, seemingly impossible challenge: elevation. While the Atlantic and Pacific Oceans sit at sea level, 0 feet, the land in between does not. Panama's mountainous terrain sits high above sea level. The engineers were faced with a dilemma. Ships cannot sail through mountains. To solve this, they didn't flatten the mountain. They decided to lift the ships over it. They designed a massive lock system acting as a water elevator. This system would hoist vessels up, carry them across the spine of the continent, and gently lower them down on the other side. The key to this entire operation is not a pump or an engine, but a lake. High up in the hills lies Lake Gatun, the beating heart of the canal. This is not a natural formation. It is one of the world's largest artificial lakes, created by damming the volatile Chagres River. This massive reservoir sits at exactly 85 feet above sea level. It serves two critical purposes. It provides a waterway for ships to cross the continental divide, but more importantly, it serves as the vital water reservoir that powers the entire lock system. Without the millions of gallons of water held here, the elevators would stop running. So how do you lift a 50,000-ton ship 85 feet into the air? You use the principle of buoyancy. This is the lock system concept. Think of a lock as a water-filled chamber with watertight gates on both ends that control ship movement. It functions exactly like a stairwell for boats. A ship sails into a chamber, the doors close behind it, and water is poured in. As the water level rises, the ship rises with it. These locks raise ships up step by step to the level of Lake Gatun, allow them to cross the mountains, and then lower them back to sea level on the opposite side. What is truly astonishing about the original canal design is its power source. You might expect massive electric pumps screaming to move that water, but you would be wrong. The original locks use no pumps whatsoever. Instead, the water flows entirely by gravity. Engineers built giant underground culverts, tunnels large enough to drive a train through, inside the concrete walls of the locks. Gravity pulls water down from Lake Gatun into the lower chambers. Huge valves control this flow, allowing millions of gallons to rush from the lake to fill or empty the lock chambers. It is a sustainable engine powered by nature itself. The journey begins on the Atlantic side. Ships enter from the Caribbean Sea, navigating the approach channels toward the famous Gatun locks or the newer Agua Clara locks. This is a high-stakes maneuver. The margin for error is razor thin. Before a ship can even touch the locks, a specialized canal pilot must board the vessel. For the duration of the transit, this pilot takes full legal and navigational control from the ship's captain. They know every current, every turn, and every hazard of the canal. It is one of the few places on Earth where a captain surrenders command of their own ship. As the ship enters the narrow concrete chamber of the lock, it gets some help. On the lock walls, you will see silver electric trains moving in tandem with the vessel. These are the mules. They are electric locomotives that attach to the ships via heavy steel cables. Despite their name, they don't pull the ship forward. The ship uses its own engines for that. Instead, the mules act as stabilizers. They keep the ship centered and steady to prevent collision with the concrete walls, with only inches of clearance on either side. These mechanical mules ensure the gentle giant doesn't scratch the pate. The ascent to the lake is not a single leap. It is a 3-stage process. Imagine a giant staircase of water. In Chamber 1, the ship enters at sea level. The massive gate closes behind it. Water rushes in via gravity, and the vessel rises. Once the water level matches the next step, the gate in front opens. The ship advances into Chamber 2, and the process repeats, lifting it higher. Finally, in Chamber 3, the last lift brings the ship a full 85 feet up, matching the level of Lake Gatun. The gates to the lake swing open, and the ship is now floating on top of the continent. Now elevated, the vessel begins crossing the divide. The ship sails across Lake Gatun, covering roughly 20 miles of the total journey. This is the most scenic part of the transit. The ship navigates through submerged valleys and past hilltops that were turned into islands when the region was flooded. It is important to note the water chemistry here. The lake contains fresh water, not salt water. This creates a unique aquatic environment, where ocean-going vessels briefly wash their hulls in the fresh rainwater of the rainforest before returning to the sea. Leaving the open lake, the channel narrows dramatically. The ship enters the Culebra Cut, also known as the Guiled Cut. This is the most treacherous and historic section of the waterway. It is the narrowest, most difficult section, slicing directly through the Continental Divide mountain range. This is where the engineering battle was fiercest. Over a century ago, thousands of workers excavated rock and shale here, battling landslides and disease to connect the lake to the Pacific side. Every inch of this canyon was carved by human determination. After passing through the spine of the mountains, it is time to return to sea level. The descent on the Pacific side mirrors the ascent, but with a slight twist in layout. First, the ship reaches the Pedro Miguel Lock. This single-chamber lock lowers ships 31 feet in one step, dropping them into a small intermediate body of water called Miraflores Lake. From there, the vessel sails a short distance to the Miraflores Locks. These final 2 chambers lower vessels another 54 feet in 2 steps, bringing them back down to the level of the Pacific Ocean. The mechanism that seals these chambers is a marvel in itself: the gates. These are not simple wooden doors. They are massive, hollow steel structures standing up to 82 feet high and 7 feet thick. They function as watertight doors, holding back the immense pressure of millions of tons of water. Despite their colossal weight, they are perfectly balanced. Originally powered by 25 horsepower General Electric motors, the gates open and close like double doors. They are so precise that they meet perfectly in the middle, creating a waterproof seal that has held for over 100 years. For decades, the size of the locks dictated the design of the world's ships. This standard became known as Panamax. To fit through the original locks, a ship could be no more than 106 feet wide and 965 feet long. Naval architects around the globe built vessels specifically to these limits to ensure they could use the canal. However, as global trade grew, so did the ships. Vessels exceeding these dimensions were classified as post-Panamax. They were too big for the canal, forced to take the long, expensive route around South America. Panama knew it had to evolve. In 2016, the canal underwent a historic transformation. The expansion, a massive construction project, added a third lane of locks to accommodate larger post-Panamax vessels. These new locks, the Cocoli on the Pacific and Agua Clara on the Atlantic, are bigger and deeper. They also feature a completely different design. Unlike the miter gates of the old locks, these feature innovative rolling gates that slide out from the wall instead of swinging like doors. This evolution allowed the canal to remain relevant in the age of megashipping. The expansion also solved a critical environmental problem: water consumption. Every time a lock empties, millions of gallons of fresh water are flushed out to sea. To address this, the new locks utilize water-saving basins. Next to each lock chamber are 3 large reservoirs. These allow 60% of the water to be recycled into storage basins from each ship transit. Instead of dumping all the water into the ocean, it is saved and reused for the next ship. This innovation allows the new locks to move bigger ships while using less water, conserving Lake Gatun's precious freshwater supply. The canal is a machine that never sleeps. Navigation and time are money in the shipping world. The canal operates 24/7, year-round, ensuring the flow of goods never stops. A typical transit takes an average of 8 to 10 hours from ocean to ocean. But this convenience comes at a price. Ships pay tolls calculated based on weight, cargo type, and vessel dimensions. For a massive container ship carrying thousands of boxes, the toll can run into the hundreds of thousands of dollars, a steep price, but still cheaper than the fuel and time required to sail around the continent. The impact of this waterway extends far beyond the borders of Panama. It creates a massive economic impact. The canal handles approximately 6% of all global maritime trade. It is the artery that connects the factories of Asia to the consumers of the United States. It is critical for Asia-US East Coast routes, significantly reducing fuel consumption and shipping costs worldwide. If the canal were to close, prices of goods around the world would rise, and supply chains would crumble. It's a choke point of the global economy. Surprisingly, the survival of this industrial marvel depends on nature. This is a story of environmental stewardship. Because the canal relies on gravity and fresh water, it depends on rainfall to continuously refill Lake Gatun's water supply. If it stops raining, the ships stop moving. Therefore, the health of the surrounding jungle is vital. The roots of the forest act as a sponge, regulating the water flow. Panama protects the surrounding rainforest to prevent deforestation, which would threaten the water system. The canal creates a unique incentive. To keep the economy flowing, they must keep the forest standing. As the ship clears the final lock and its bow cuts into the Pacific, we are left with a sense of awe. In summary, the Panama Canal is more than just infrastructure. It creates a remarkable bridge of water 85 feet above sea level, harnessing the simple powers of gravity, fresh water, and massive steel gates. It remains one of history's greatest engineering achievements, a testament to human ambition that has been moving global commerce efficiently for over a century. It is the place where we moved mountains to unite the oceans.